we go with our second day of electron configuration. Now we've seen some of these rules both yesterday and the previous day when we went through and did one of those POGLs with the electron configuration. And one of the first things that we notice is Aufbau's principle. We talked about that yesterday. Remember that Aufbau means building up in German. So you need to make sure that when you're putting in electrons for multiple electrons within an atom, that you fill up those lower energy levels before you come back in and fill up the high energy levels. And so it's just like if we're walking up the stairs, you're not going to just go from step 1 to step 8. You're going to go from step 1 to step 2 to step 3, etc. So it's the same sort of thing, that you have to fill up the lower energies before you move to the higher. What we're going to end up seeing is that order of building up, I'm not going to go very far, but it's the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s. Anybody remember what comes after the 4s if you look at your periodic table? Awesome. 3d, then 4p, etc. That's that order of building up, which means that something like a 3d actually has more energy than a 4s. So that's what that means. That's what Aufbau's principle tells us. Well, we've also got something known as Hund's rule. Now, actually they did call it that when you guys did the POGL, and that was when we had those boxes, and we said, and these boxes represented orbitals, and we said that in order for those electrons to go in there and fill up those orbitals, what happens is they fill up orbitals of equal energy one at a time. So let's pretend that this is the 3p. I'm just making this up. Let's pretend that's a 3p. That means that this orbital in the 3p has exactly the same amount of energy as this orbital and exactly the same amount of energy as this orbital. So you do equal energy one at a time before coming back and pairing up. Now, I like to think about this as being our school bus rule. When you guys, there's a big group of people that are supposed to get on the school bus. What do? You all get on there and say, woohoo, I have my own seat. So somebody's going to sit in their own seat. Another person gets on and says, yippee, I've got my own seat, and sits down in their own seat. Another person comes in, yay, I've got my own seat. So everybody goes in and grabs their own seat first before then things start getting crowded and other people come on and they have to start pairing up. So that's what Hund's rule tells us, is that they enter orbitals of equal energy one at a time before then coming back and pairing up. Okay? And then finally, our third rule that we're going to look at is something known as Pauli's exclusion principle. And this will make more sense when we start talking about quantum numbers. There are 4 quantum numbers we're going to bring up. But right now, let's just think about it as the fact that any orbital can only hold 2 electrons, and those 2 electrons within that orbital have to have different spins. It is not possible for within this orbital right here for both of them to be up arrows. Notice I do like little cheater arrows. I do half arrows just because I'm lazy and it's hard to fit them in there. But those are just up-down arrows is all I've got. So not possible, according to Pauli's exclusion principle, not possible for 2 electrons within the same orbital to have the same spin. They have to have opposite spins, different spins. And there's only 2 possibilities, up or down is how we represent those with arrows. Okay, so those are our rules that we're going to be looking at. Hopefully going through orbital diagrams will be fairly easy for you guys because you've seen this a little bit before. So the first thing I want to remind us about is what our number of orbitals are for each of these sublevels. So I think if I were you guys, I would probably find a little space on my notes to just jot this down somewhere. How many orbitals does an S sublevel have? 1. I am going to represent that with 1 little box. How many does a P have? 3. So we represent that with 3 boxes. And notice all 3 of those boxes are attached together. What about a D? 5. And then finally your F? 7. Okay, so we've got that for our orbitals. Now, if we have a situation where let's say in a p. Let's say that there are only 2 electrons in that p. What do you think? Do you have to still show all 3 boxes, all 3 orbitals? Yeah, you do. You would have to show all 3 of these, even if you only had 2 electrons. So it's showing the orbitals, and then you can show the electrons within it. Okay, so we do have an example here for sodium. I'm going to let you guys stare at that on your own. Notice that because it's computer generated, you've got this nice font and all of this, it's just dashes. It's really hard for us to do that when we're doing our handwriting because it's hard to represent a space right there. So what we do instead is we typically draw boxes, but sometimes you might see them as dashes because it's easy to show the spaces. Here we want to draw our orbital spin diagrams. In order to do this, we need to know the electron configuration. So somewhere, I bet it said this in here, is that we are going to go ahead and represent these orbitals only after the last filled noble gas. So in other words, we're going to use our shortcut method that we learned yesterday, which is showing that noble gas configuration. So if I were to look at nitrogen, it's not really a big help to us to use a shortcut, but if I were to do the long method, nitrogen, 7 electrons, it would be 1s2, 2s2, 2p3. My shorthand method, instead of saying that 1s2, I would just show my helium, and then after that is 2s2, 2p3. Now, when you guys are writing this down, if you want to think about spacing, I'm going to have 2 things written for each of these. Now I'm going to put my orbital spin diagrams on top of that, so I'll always have my electron configuration below that. For this, rule tells us we do our most recent noble gas, and then we show our orbital spin diagrams for everything since then. So I look at my 2s. I know for my s's, I'm going to draw 1 box. For my 2p, my p's, I draw 3 boxes. What I have just shown is all of the orbitals for both of those sublevels, for my s and my p. Now I can go through and illustrate the electrons within those orbitals. So I see that in this 2s, I've got 2 electrons. So by convention, and I know that the POGL that we did the other day actually did the opposite. Rarely do you see the opposite. I've got another situation where the opposite is shown, but usually it's the up arrow. Just by convention, we show the up arrow first and then the down arrow. So I would say up, down. Those are those 2 electrons within the 2s. So satisfying Aufbaus, we have filled up the 2s, so now we can go to a higher energy of 2p. There are 3 electrons. Think about the school bus. Yippee! Everybody gets their own seat. So there's up, up, up in those 3 different orbitals. Okay, I'm going to keep moving on because this is a time crunch to get this finished. Let's go to our oxygen. Oxygen, again, it's going to be your helium. We're going to 8 valence electrons. It's right next to nitrogen. So here it's 2s2, but it goes all the way over to 2p4. So that takes care of those 8 valence 8 electrons because you've got 2 within helium as well. So again, our boxes are going to look the same, but what we're going to see is that our electrons are a little bit different. We've got an up-down for our 2s, but our 2p, up, up, up. And then that 4th electron, he has to share a seat with somebody on the school bus. So we just go back to that first one, and it's a down arrow. Pauli's exclusion principle tells us has to be an opposite spin. Okay, manganese. Getting a little tougher now. We're looking at number 25. Most recent noble gas is argon. After argon, okay, you guys tell me, what comes next after argon? 4s, then 3D. Awesome. Okay, so we've got a 4s2, 3D, and I have to count here. 1, 2, 3, 4, 5. Going over to manganese. So when we draw our orbital spin diagram, I am going to say that I've got 1 box here. I have got 5 boxes for my D. So now it's going to be up, down for my S. And then I've got 5 arrows up, 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 up. So that's what my orbital spin diagram looks like. And the last one that we're going to do, we're going to go over to gadolinium, which is number 64 down there in your lanthanide series, your F block, so number 64. And for this, I don't know if this is going to show up on the video or not. Hopefully it does, but I'm going to bring up a periodic table underneath my document camera, so we'll see if this works for you guys at home. Okay, so we are going right here to gadolinium, and I have a feeling this isn't showing up on the video, but we're going to gadolinium. So what is your most recent noble gas for number 64? Xenon number 54. So you're going to go to 54 xenon. Then after 54, you have to go to number 55, right? So what are you going to call this? 6s2, that takes care of these two guys. Then after number 56, where are you going to go? Good, your 57, which is your 4f, right? So sixth energy level, or sixth period, when you come down to your F block, it goes to the fourth energy level, fourth period. So we're going to say 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be a 4F8. And then we're done with that. So going back to this, hopefully we're able to see that at home. We're going to say that we've got xenon, 6s2, 4f8. So one block, one orbital, 7 orbitals. And this is going to be up, down, up, 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 down. Okay. Are we good there? Any questions on that? All right, so hopefully that made sense to you guys. So now what we want to do is we want to work with some electron configurations for ions. And remember, we've learned about ions from last unit. We just said that they're going to be charged atoms. So if an element gains or loses electrons, then it no longer has a neutral charge, it has a charge to it. So ions, when they do this, they are going to gain or lose electrons so that they become more chemically stable. More chemically stable. So, in other words, they want to get a full outer shell because atoms are most stable with a full outer shell. So that's our octet rule. There's a place for you guys to write that down. So atoms are most stable with a full outer shell. Now the ions that they form, they can either lose electrons or they can gain electrons. Now here's the tricky part, is you have to remember electrons are negatively charged. So if you lose negative particles, what's the charge become? It's more positive. And if you gain negative particles, it becomes more negative. So it kind of seems like the opposite in some respects. So when you lose electrons, you become more positively charged. That is known as a cation. Anions are negatively charged ions. Maybe you want to remember this as cations. There's your positive. And anions. I will underline the N for negative. So you need to remember the charges of those ions. Okay, so let's go ahead and do some electron configurations for these guys. First one, it says the fluoride ion, which is F-1. Well, I'm covering up right now the -1. You can't see that at home, but right now I'm just looking at the F. Let's go ahead and write out the electron configuration for an F. I'm going to do this the long way. I'm not going to do a shortcut method on this, just because for teaching reasons, I'm just trying to show you why this works this way. So if we look at F, we see it's going to be 1s2, 2s2, 2p5. Well, according to what we just said, it will be more chemically stable, and I really just kind of jumped ahead, more chemically stable if it has a full outer shell. Why is that called the octet rule? 8 electrons is a full outer shell for most things. Tell me one element it's not that way for. Helium, hydrogen, right? They want just 2 electrons. That's all that first energy level can hold. That is a full outer shell. Most others would be 8. So here we see that we've got 7 valence electrons, and hopefully you guys remember that from yesterday. Our highest energy level is the second energy level. How many electrons do we see? We see 7. So that's not a full outer shell. What does it need to do to get a full outer shell? Gain 1 more electron. If it gains 1 more electron, it becomes -1 for its charge. So we're just going to say that this becomes 2p6. That would be our electron configuration for the fluoride ion. So you guys, you figured out why that -1 is there. That -1 is given to you. You know that it gains an electron, but you looked at this and even saw that it should, to become more chemically stable, it needs to get 1 more electron. Okay, let's look at strontium with a +2. If I were to just write the electron configuration just for neutral atom of strontium, I would end up seeing, and strontium is number 38. So I would see it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p6, 5s2. So that is a neutral atom of strontium. Pretend you weren't even told that it formed a +2 charge. You looked at that and you said, what does strontium need to do to become more chemically stable? How many valence electrons does strontium have? 2. So we look at this and we see that this is your highest energy level, those 2 electrons are valence electrons. So it could try and gain 6 more electrons. That sounds cumbersome. That would be a hard thing to do. What would be easier? Losing 2. So hopefully you can see that those are the 2 that it loses. Why? Because those are on the outside. Those get knocked off pretty easily. The ones inside of that do not get knocked off. Those stay there. Those are your core electrons. So now, how many valence electrons do you notice that strontium has? 8. So when it forms that strontium with the +2 ion, it has 8 valence electrons. The 4th energy level is the highest, and there are 8 valence electrons there. Let's stop and look at this. Let's go back to our fluoride ion. That looks similar to me to something else. I see 1s2, 2s2, 2p6. What else has that electron configuration? Neon. So look at your periodic table. You see that those 10 electrons, neon has 10 electrons. So that is isoelectronic with neon. It has 10 electrons as well. So what do you think isoelectronic means? Good, good. So isoelectronic means same electron configuration. There's a place to write that down. Same electron configuration. And what we end up seeing is that atoms are most stable when they get the same electron configuration as a noble gas. So now going to the strontium with a +2 charge, when it lost those 2 electrons and ends up having a 4p6 as its final electron, which one has a 4p6? Which one? Krypton. So the strontium ion is isoelectronic with krypton. All right, now we get to our transition metals. Again, I'm going to be pointing to a periodic table that you can't see at home, but in fact, I'm just going to pause. We just looked at our periodic table and we saw all of the valence electrons for your main or representative group elements. It's 1 through 8, right? Starting with your alkali metals and then going to, I got it. and then going to your noble gas is number 8. So what ends up happening now is we look at our transition metals. Those we didn't ever say anything about. We didn't assign valence electrons to those guys. But what we end up seeing, if you looked at your electron configuration, you would always see that from your S, you've got an S2, whatever that energy level is, you've got an S2. So for the most part, we're saying that you've got 2 valence electrons. Well, what's going to end up happening is when they form charges, when they form ions and lose electrons, they're going to form positive charges. They lose electrons that are in the outermost energy level. Outermost energy level. So let's see how I can put this in here. The valence electrons are the electrons that are lost. In other words, the outermost. Hold on. But it is not necessarily not the highest energy. So again, if you remember back to what we said about Aufbaus, it doesn't always follow the same rule. And the way I'll illustrate that is with iron with a +2. So if I were to just write the electron configuration for iron, and again, I'm going to do this a little long way just so I can kind of illustrate this. So just iron is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. Give you a chance to catch up there. So that is my electron configuration for iron, a neutral atom of iron. But when it forms a +2, what does that mean? Is it gaining or losing electrons? Losing. It is losing 2 electrons. Do you guys see which electrons it's going to lose? Good. It's going to lose that outermost energy level, the highest, the outermost energy level, that 4th energy level. However, Aufbaus' principle tells us the 3D actually has more energy. And we could go back to thinking about the situations with your sublevels. The reason it has more energy is because it's more complex. Those D sublevels are a lot more complex. There's more energy associated with a 3D than there is with a 4s. But the electrons come from your 4s, so that's what we end up getting. So your electron configuration, if you were to do a shorthand notation, it would actually be argon and then 3d6. That is what an Fe +2 looks like. All right. So that is looking at electron configuration for ions. Now, we can also look at something known as diamagnetic and paramagnetic. And with these, this has to do with you know, I'm not going to hold you responsible for this, but it has to do with the fact that diamagnetic substances, they oppose a magnetic field, whereas paramagnetic substances actually produce a magnetic field. So an element is said to be diamagnetic if there are no unpaired electrons. That's what you're thinking about, is your paired and unpaired electrons. So diamagnetic, there are no unpaired electrons, they're all paired. And paramagnetic is when you do have unpaired electrons present. So in order to do this, you need to kind of at least think about orbital spin diagrams. So let's work with magnesium. And I can go ahead and use my shortcut notation on these. Magnesium, number 12, I see that my most recent noble gas is going to be neon. After neon, I have a 3s2. So now with that 3s2, when you draw your orbital spin diagram, it is up-down. Do you have any unpaired electrons there? No. So which one's it going to be? Diamagnetic, meaning it opposes a magnetic field, is what happens. If we were to go through argon, or not argon, if we were to go to iron, we would see that it's argon. And then after argon, we went to 4s2, and then 3d6. So for this one, we've got up, down. for your 4s, and then for your 3d, up, 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 down. Do you have any unpaired electrons? Yeah, all 4 of these are considered unpaired electrons. That's what we mean by unpaired electrons. So this one would actually be considered paramagnetic. It produces the magnetic field. All right. For the rest of these, I'm not going to draw my orbital spin diagrams. Instead, I'm just going to do the electron configurations. So cadmium, what you end up seeing is you get krypton, and then you get 5s2, and then 4d, what is cadmium? 4d10, thank you, I should know that. So 4d10, do you see any unpaired? No, you can even do that without actually seeing that orbital spin diagram. You can probably look at your electron configuration and notice that would be diamagnetic. And last one, we've got phosphorus, which is going to be neon, and then you've got a 3s2, and then a 3p3. So in that case, do you have any unpaired electrons? Yes, you do. So that one's paramagnetic. All right. So that's what we've got with those things. We've got 2 other little situations to work through, and then we will be done. We're doing great with time, so lots of time for questions. Last little one that we'll, last couple. First of all, here it's just, you don't have this in your notes, but I just want you guys to think about this because we're about to look at some ions in the next one. So again, think about why it forms the charge that it does. If you were looking at potassium, you see it's an alkali metal. What do you know about all of your alkali metals? What's the chart? What's the number of valence electrons? 1. What's the easiest thing to do? Lose 1 or gain 7? Lose 1, so it becomes K with a +1 charge. Gallium, it's over there underneath aluminum. So how many valence electrons? 3. Easiest thing to do? Lose 3. So it becomes gallium with a +3. Cobalt, ooh, there's a transition metal. What do you know at this point about your transition metals? It's going to lose 2 because it's got 2 valence electrons. So +2, same thing happens with zinc. So that's all we're going to say about those guys, because I just want you to see where these charges come from. These are the most common ions that are formed for these guys right here. So what we want to do now is we want to think about the color of solutions. And when we do labs, we're going to work with a whole bunch of solutions, and most of them are going to look just like water. Not very exciting. Most solutions are clear in color, but sometimes they will be colored. And the way that that works is that the ones that have unpaired d electrons actually exhibit a color of some sort. Now, there's no way to tell what that color is just based on your electron configuration, but you know that there's going to be a color associated with it. So this is kind of neat that we've got something like electron configuration can predict the things that we're naturally seeing with all of these elements and ions out there. So for the first one, it says predict which of the following will produce a colored solution. So potassium with a +1. If we were to write our electron configuration for this, and we can go ahead and do a shortcut. We know that it's potassium's number 19, so we're going to go to argon. And then 4s1. Again, you're thinking about paired or unpaired d electrons. Now, pretend maybe there's d electrons in there. Hopefully you can look at your periodic table and say, no, we haven't even gotten to the d block yet. But suppose there were that chance, do you think that they'd be paired or unpaired? They're paired. If you've got them in an electron configuration of a noble gas, they are paired. So you would never have any unpaired in there. So do you see any unpaired d electrons? Nope. So what color is this going to be? Clear. All right, gallium with a +3. So for gallium with a +3, again, we're going to go to argon. And we're going to go to 4s2, 3d10, 4p1. Any unpaired Ds? Nope. So it is clear. All right, cobalt with a +2. So, and you know what I'm not doing really good here? Here's what I should be doing. I should be showing you, yeah, we just did potassium, that's a +1. Gallium, that's a +3. But again, it's not losing anything from those D's. Okay, cobalt. We're going to look at cobalt, which is number 27. Again, we're going to say it's argon, and so then we get to our 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. Well, it's cobalt with a +2, so those guys go away. Any unpaired d electrons? Yay, we get to see some color. All right, and the last one that we've got is our zinc. And again, this is just right there at the end of your 3Ds. So it's going to be your argon 4s2, 3d10. But again, hopefully you guys are also seeing that when it gets that +2 charge, it's losing it from the outermost energy level electrons. So here in this case, we've got all of our d electrons are paired. So again, it's going to be clear. Okay, good to go on this, looks like. Last little thing that we want to look at now is some exceptions to writing electron configuration. Now, these exceptions that we're going to be looking at only apply to transition elements. And more specifically, it's going to apply to just two little groups, two little columns within the transition metals. So, for certain reasons of special stableness, I don't know if that's really a word or not, but it's more chemically stable if these electrons, if these atoms have electrons in fully filled or half-filled orbitals. So let's see, it says it right here, half-filled and fully filled orbitals. That makes it the most chemically stable. Has to do with that electron repulsion, which we haven't really touched on yet, but those electrons, if everybody can be in their own seat in the school bus, then that's pretty stable. If everybody's in the school bus and they're all paired up, that's pretty stable. But when you get some kind of filled, some kind of not filled, that's when it's unstable, is what that amounts to. So what we're going to see is that, just like it tells you here, everything in your transition metals beneath copper and chromium are going to fit this category. So we're going to do the first two here. If you were to write the electron configuration for copper, and I'm going to go ahead and use noble gas configuration, my shortcut method. So I look at copper, number 29. I see that I'm going to go to argon. And then after argon, I come to 4s2, 3d9. So I can't reach this high. I'm going to put this underneath just so I don't have to stand on my tippy toes. I'm going to go ahead and draw the electron configuration, the orbital spin diagram for these guys. What you might think is that, yeah, up, down, and then we've got these 9 electrons up, 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 down, 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 down. Well, that's not really that stable to have 9 out of 10 or 4 out of 5 orbitals filled. So instead, what happens is half-filled or fully filled is actually more stable. So to have it become up, in other words, one of these guys goes over here, so it's up, 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 down, 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 down. So our actual electron configuration that we would expect would be argon and 4s1, because one of those electrons went over to the D block to be able to fill that up, and then 3d10. Okay, so there's one exception. We could do a very similar thing for chromium, and if you look at chromium, it's number 24. So number 24, I'm not going to draw my orbital spin diagrams on this, we're just going to do the electron configuration. So we would see that we've got argon, and then 4s2, 3D4. That's what you might expect. But then you take a closer look and you notice, aha, this is just kind of partially filled. It's not half filled and it's not fully filled. By getting one of these guys to move over, we can get it half filled. So argon 4s1 3d5 is actually more stable than the other. Now, notice that your silver is just directly beneath your copper, so it would follow that same pattern. I'm going to go ahead and show you this this little application where we can see what's going on with the filling of these orbitals. And it's kind of dark. I don't know if you guys can see these arrows here. This is that other situation where, and it's so rare to see it like this, but they actually do the down arrows first instead of the up arrows, but it's the same sort of deal. So for hydrogen, you've just got one electron in the 1s. For helium, your 1s is filled with an up-down. Then we could go to lithium, and you see you've got 1s2, 2s1. And here's our beryllium, 1s2, 2s2, 2p1. And it keeps going to boron, carbon. Now that was Hund's rule. Everybody got their own seat on the school bus before coming back and filling in. And this is kind of hard to see. But now we just got to neon noble gas configuration. Everything's filled in that 2p. Now we're getting up to our 3s. And I'm going to kind of go through this quickly just so that we can get to our Ds, because that's what I want to show what's going on. And it takes a little while for this to catch up. Okay, so now we're at titanium. We just did scandium and titanium, vanadium. There's chromium. Watch what happens. Oh, see that electron? There it goes from the 4s to the 3d. So it goes now, instead, it's actually a 4s1, 3d5. We can do a few more and get to make sure I'm not going too fast here. There's copper. We're going to have the same thing go on. So those are our exceptions, where now it's actually more stable to have one that's half filled and one that's fully filled. All right, I think that is it for today's notes.